Hello, good morning. Hello, good morning, guys. Can you hear me well this morning? You can let me know, please.
Yeah, I can hear you.
Oh, you can hear me. Perfect. So, well, today we are going to be getting into capacitors, but I'm just wondering, like, if you have any questions from the last meeting that we had. Anybody have any questions about our, like rectification, any of the formulas, any of the calculations at all? Everything is mute. So I'm going to assume that everything is okay. Okay, guys, so what we are going to do, like the plan this morning is the following, okay? First thing that we are going to do, we are going to spend about like 30 minutes going through a PowerPoint together about capacitors. Now, before, I start these ideas, this PowerPoint, I have a question for you, and I want you please to answer me. Have you covered this topic in AC theory? I mean, have you covered capacitors in AC theory?
Yeah, we had a short module on it, but wouldn't hurt to do it again.
Yeah.
Okay, so why don't we approach the topic, instead of me teaching you everything new, why don't we have a discussion about the PowerPoint instead, okay? I think it would be more fun, just to have a discussion about it, and then I can help you to fill in the gaps. Would that maybe be less boring than me trying to explain a PowerPoint that maybe you have seen already?
Yeah, sounds good to me.
Okay, so let me show you that. Let me show you the, okay, so that's the PowerPoint right there. Just wait a second, I just have to, perfect. Hey, welcome to those guys that just joined us. So we have a pretty good attendance this morning.
I don't know if it's just me, but just looking at the beginning of your slide there, it might not hurt to just go through because it looks like it's a little more in depth than what our theory one was.
Yeah, I agree.
Yeah, the theory I think just really dealt with kind of the math of it.
Yeah.
Okay, perfect. So I'm not going to be getting super deep into it. We're just going to cover like the basic on how a capacitor is made. That's number one. Okay, so we are going to deal with the following today then. Okay, so we are going to cover number one. Okay, so let's see. Number one here. What is it? What is the factors? What are the three factors that determine capacitance? So any ideas about that? What factors determines capacitance in a capacitor?
The size of the plates.
Perfect, the size of the plates. So we don't have to rain over wet. What else?
Is it the space between the two plates?
And also the space between the two plates. And that explains why is it that when you are doing the math between capacitors in parallel and capacitors in series, why is it that in parallel they add up, while in series they add up reciprocally, right? Like in a reciprocal manner. Also, like capacitors, they remain charged because of what? I mean, they retain an electrostatic charge. And because they have an electrostatic field, that's why that they remain charged once the power source has been removed. Okay, so, and the other thing is, we're going to, well, we're not going to get deep into discussing the difference between non-polarized and polarized capacitors. It just suffices to know that polarized capacitors, like the one that we are going to be using for our projects, at least, you know, for project 4, it is a capacitor that is polarity sensitive. So the positive has to be connected to the positive terminal and negative to the negative terminal. And what do you think is going to happen if you don't do that on a polarized capacitor?
It's going to short out.
Yep, perfect. So it's going to happen that it's going to overheat, number one, and also it's going to short out. It's going to explode pretty much. And then in the case of non-polarized capacitor, that's something that you are going to use when you go to the motor shop and do AC motors. And you do, like, there's a component on AC motors where you have a start, I mean, like, sorry. So it has like a start in a motor with a capacitor, like motor start capacitors. And the capacitor in that instance on on a capacitor starting motor is going to be connected in series. Okay, so let's get going from there. Let me see if I'm going to be able to. Perfect. Okay, so let's begin, guys. Or let's keep going. So what about this? Calculating the values for series and parallel connections of capacitors. Is that something that you cover as well?
Yes.
Yes, that's something that you cover. So we only have to, I mean, just talk about the reason on why, you know, those values add up the way that they do add up. Okay, so let's keep moving then. So this other idea of calculating the constant, RC time constant here, that's a topic that we are going to cover later on, because that's the way that the capacitor is going to be charging and discharging. It's going to be charging and discharging, describing, or at an exponential rate. So because of that, I mean, this is going to be project 7, if I recall well. And because it's project 7, I'm just going to wait until we get there in order to cover that topic. That way, it's going to be fresh information once you get to that point.
Hey, sorry to interrupt you there. I was just wondering, I was writing it down, the 3 factors. It was the size of the plate, the space between the plates, and what was the third one?
Perfect. That's a great question. It's going to be like the distance between the plates.
I thought, so that's what I have, the size of the plates and the space between the plates.
Okay.
Okay.
Oh, sorry. Size of the plates, the distance between the plates, and also the type of the dielectric material.
Oh, okay. Thank you.
You're welcome. Okay, so let's get moving, guys. So as I was mentioning, like this last topic here, the capacitor being charging at an exponential rate, okay, charging at an exponential rate. Oops, I don't know why this keep happening with, I don't know, I'm having some issues. Okay, now it's good. Capacitor charging at an exponential rate and discharging at an exponential rate as well. That's something that that's something that you are going to do in the shop, and that's something that we are going to cover, as I said, once we are getting prepared to do that lab, or at least to discuss it. Like today, what we are going to do is that we are going to, as I said, as I mentioned before, go through some main points about capacitors, and then I prepare on multisim a small rectification circuit where we are going to see how the capacitor behave in the circuit. You know, how is it going to be able to filter the ripple voltage from your bridge rectifier. So let's keep moving then. Okay, so here on this topic, we are told that a capacitor will perform a variety of jobs. Have you ever heard this new topic? You know, this is something that you are going to be doing in theory for sure. Powell factor correction. Have you heard that before?
I heard it,
No.
yes, but haven't really done with it anything with it.
Okay, so the important thing is, this is something that you are going to cover in theory. And because we're not going to be doing any labs about Powell factor correction, I mean, in level 3, yes, you will do it. But in level 2, we don't do Powell factor correction. However, just to, you know, give you an idea on what it's all about, we have, when it comes to Powell factor correction, we have the following. Remember that on the oscilloscope, or well, you know, whenever we are doing math, whenever we are doing the trigonometry for AC theory, remember please that the horizontal lines means, okay, so let me do it this way. I just want to do it in such a way that it's going to be easy to understand, okay? So let's draw the power triangle. Do you heal the power triangle before? Right on the power triangle, you have the following values. The hypotenuse is called your V8, your volts amps. While here at the bottom, where we have the horizontal line, that one is our true power, which is represented by the letter P. While the vertical line, it is your bars L, or the reactive power that you have on the inductive circuit. So far, so good? Have you seen that triangle before?
No.
Nope.
Okay, so I just don't want to go ahead of theory, but this is something, this is what is called the power triangle. And in any inductive circuit, okay, in other words, in any coil, in any motor, in any circuit that uses coil wire, you are going to have those three elements in place in order to produce your useful work. Now, the thing is that here we have an angle difference between your true power and this is called true power, this one at the bottom here. That's our true power. So there's an angle difference between the true power and your volt amps calculation. We are used to the idea that if we have, let's say, 120 volts, and we multiply 120 volts times, let's say, 5 amps, we are used to the idea that we are going to have an output power or an input power, which is going to be equals to 600, right? Is that what we have? So we would do 120 times 5, that would be equal to 600. Now, this 120 volts times my 5 amps, yes, it is equal to 600, and that's going to be 600 what? Volt amps. Now, that is not the output power, okay? And I'm not talking in this case about efficiency. I'm talking about another element here. In this instance, this other element here, which is the true power, this is going to be the real useful work which is being done in the circuit. This VARS L, it is the amount of power which is being used to produce your magnetic field. So now, something which is important when it comes to Powell factor correction is that you are going to have your VARS C, which is the reactive power which is produced by the capacitor. is going to be in the opposite direction of your vars L. Because of that, the vars L effect in the circuit is going to be canceled by the vars C, and then they are going to reduce the value of this angle theta, which is called the Powell factor, which is the inverse of the cosine. But that's just to give you the heads up, okay? That's what's happening there. That's why you can use a capacitor for Powell factor correction, because it's going to be able to cancel. Hello. Good morning to the guys that just joined. So we are talking about like one of the uses of capacitors. And we were just exploring pretty quickly the use of Powell factor correction, okay, of the capacitor being used as a device for Powell factor correction. But we are not going to spend a lot more time on this, rather than just knowing that because the vars L are being canceled by the vars C, we are going to be able to reduce this angle theta, and we are going to be able to obtain a V times A that is very close to the actual true power, which is going to be produced by the circuit. So that's just to give you the heads up, okay? So now, the most important part to us is going to be the following. In electronics, in our case, the most important aspect is to know that indeed the capacitor stores an electric charge. Why is that important to know? We are going to see it with the oscilloscope. The capacitor is like a see this max value. If any questions? Okay.
You kind of just cut out there at the end there. I don't know.
Oh.
You were just kind of stuttering.
Oh, it wasn't just you, man? Yeah, because I'd say I couldn't hear you either.
Yeah, that last part was breaking up.
Same.
What was the last part? When I was talking about that,
storing an electric charge?
Yeah.
Just at that part. Like, we started that
Oh,
part.
okay, perfect. So what I was saying was, thank you for letting me know. What I was saying is that the capacitor is going to store an electric charge, and it's going to behave as a holding tank. Okay, so because the capacitor is going to behave as a holding tank, because of that, when the pulsating DC reaches its peak value, right here, when it reaches that peak value right there, the capacitor is going to be fully charged. Once the capacitor is fully charged, you gotta keep in mind that this pulsating DC is always behaving, is always describing the same pattern. However, because now the capacitor, you have your holding tank, which is the capacitor, which is charged with electrons. Now the capacitor, when this DC is coming down in value, or it is decreasing in value, is going to be able to discharge. It's going to be able to discharge through the load. And because it's going to be discharging over time, you are going to be able to see something like this. You're going to be able to see on the oscilloscope that instead of having that pulsating DC is going to be filtered, and the amount of ripple voltage that you are going to get at the end is going to depend on two factors. Number one, the capacity or the capacitance of your capacitor, and also, what's the size of the load that you have connected to that capacitor. In other words, just to keep it simple, because the capacitor stores energy, is going to be able to supply energy to the circuit or to the load when your pulsating DC is falling down. Okay, so it's going to use that stored energy in order to produce close to a perfect DC signal. Any questions about that? And because we are going to be using that, storing electricity in the, storing, electricity in an electrostatic field, we are going to use it pretty much, as it says here, as an electronic filter. That's what we are going to use it for. I mean, in our case, that's what we are going to do. We are going to use it as an electronic filter. But also, you got to keep in mind that filter, it refers also to audio, like audio equipment. Sometimes you are going to have kind of a noise that we don't really like very much, like a noise. And with the capacitors, you are able to filter all those noises, because then you are going to be able to have a flat input into your speakers, without having any disturbances. And that's why, I mean, that's just one example on how to use a capacitor for something other than just rectifying DC. Any questions about that? So you're very quiet.
Crystal clear.
Pardon me?
Crystal clear.
So we're good.
Yeah.
Okay, perfect. So let's keep moving. So here we have the different types. Non-polarized capacitors, they can be used, as we can see in here. Non-polarized capacitor, the reason why they are called non-polarized and they are used in AC and DC, it is because, of course, they are not polarity sensitive. So because at the end of the day, we don't have a defined polarity in AC. In AC, line 1 is going to be positive and negative at a rate of roughly about 60 times per second, depending on your frequency, right? So you don't be able to connect a polarized capacitor, which is polarity sensitive to an AC circuit. And if that happens, we know what's going to be the consequence of that. What do you think is going to be the consequence? Like if we decide like to plug in a polarized capacitor into an AC circuit, what do you think is going to be the consequence in that case?
It'll short circuit.
Capacitor blows.
Yeah, eventually it's going to heat up and then it's going to explode. Yeah, that is true. So let's move on. Now, the capacitors, what are they? You have a plate which is made of copper, it could be copper,
You're breaking up.
aluminum, it could be zinc. Pardon me?
Yeah, you're breaking up. You're just breaking up
again.
Oh, I am breaking up again? So let me check my audio settings pretty quickly to see what's going on.
It's not the audio, it's a digital static, it's connection.
Oh, okay. Wow.
You're clear now, though.
I am clear now. So I'm just gonna be making sure that just give me 1 second here, please, guys. I gotta make sure that okay, so let me check something.
Are you using Wi-Fi or an Ethernet cable?
No. Right now I had to use let me check something up. Let me see. I am using Wi-Fi because, but my Wi-Fi is supposed to be good. Can you hear me well now? Can you hear me better or about the same?
A lot better.
A lot better now?
Yeah.
Okay, perfect. Yeah, the reason why I'm using Wi-Fi is because I'm using a laptop that the college gave me, and then this laptop doesn't have an Ethernet, connection point, an Ethernet connector. So let's keep moving then. We're good now?
Yes, sir.
Perfect. Thank you for letting me know, guys.
Seems like
Perfect. Thank you for letting me know. Let me just move something around here. Okay, so let's keep moving then. Okay, good. Okay, so as I was saying then, well, we have two different plates, or excuse me, like we have two plates, and these two plates is separated by a dielectric material. This dielectric material, okay. So this dielectric material, it's as I was saying before, it's going to be one of the factors that determine the amount of capacitance that we are going to have in our capacitor. So, okay, just give me 1 second here. Perfect. So let's get moving. If you don't have any questions about that, so we can keep moving here. Okay, so let's keep moving. Do you see that on the screen?
Yep.
Okay, so what do you see right now on the screen?
Capacitors oppose a change of voltage, and a little picture of dielectric material and plates.
Okay, perfect. So the idea here, like one of the most important aspects that I just want to, it's just, sorry guys, it's just that when I change, I was changing my computer configuration and it changed my screens. I'm using like two different screens to do this. And then that's why I lost track of where I was, because the screens were changed for me. So in this instance, we got the following. We can see here. Okay. So a capacitor, what a capacitor is to do is that an impedance, I mean, when you plug in a battery with your power source, when you plug it in, right at the beginning, you are going to have a very high current, very high current in order to charge the capacitor. Once the capacitor is charged and we have the same voltage across the plates, that the same potential difference that we have on our source, the force we are going to have the current and the capacitor is going to be charged. Now, probably one of the most important aspects of this.
Can you say that again, Garcia? You lagged out there. Maybe it was just me, but I'm not sure.
No, he's
Oh no, I got it too. I just thought it was just me.
I continue breaking off.
Yeah. Are you in Dominican Republic over there?
It's on vacation.
No, I was going to say for a second, I wish, but you know, like it's. Okay, so let me take you back to this one, right? That's where we were. Okay, so I was saying the following. I said the following. I said, number one, at first, when the capacitor is connected to the power source, we are going to have a very high inrush current flowing through the wires. Why? Because at that moment, the electrons are moving at a very fast rate between the plates in order to charge the capacitor. So right at the beginning, I want you to please to be able to notice the following, okay? So can you see the slide with the 2 meters now?
Yep.
Okay, perfect.
Yep.
Yep.
So that's good. I only was making sure that I can put this computer back to what I wanted. Okay, so let's keep moving then. So now that our capacitor is like right here, okay, we got a power source connected, and because we have a power source connected, once the capacitor is charged, we can remove the power source we are going to be able to remove the power source, and the capacitor is going to remain charged. Now, the thing is, why is it that the capacitor remains charged? That would be one of the important things, okay? The reason why the capacitor remains charged is because there's an electrostatic attraction between the electrons that you have on the negative plate and the holes or the positive charges that you have on the opposite plate. Both plates are separated by your dielectric material. Were you able to hear that?
Yeah.
Okay, perfect. So now, the reason why you can see on the slide here that you have like some electrons going through the dielectric is because there's not a perfect dielectric in the world. There's not, I mean, there's nothing like a perfect dielectric. Eventually, I mean, over time, because there's not a perfect dielectric, the electrons are going to be able to flow through the dielectric material all the way up to the positive plate. Because of that, over time, the capacitor will be discharged. Okay? Now, something important here. The important thing is, in here, is that also because you have this huge attraction between the negative charges and your positive charges, that's why that you have created an electrostatic field through the dielectric, which is going to cause your charge to remain in place. So because you have this attraction, it's going to be behaving pretty much like a magnet. And that way the charges are going to stay in place. Questions about that? Well, we are good.
I think we're good.
Sounds good.
Perfect. Okay, so something important. Electrostatic, electrostatic. Static means not moving, right? And electrode comes from electrons. Electrons that are not moving. They are being held in place. So it's important to keep in mind. Okay, guys, so here, the dielectric material of an uncharged capacitor is going to have atoms, I mean, just like any other material in the world. However, once the capacitor is charged, then those atoms are going to experience a stress. The stress that they experience is that on the nucleus, we have positive charges, and those positive charges are going to be attracted closer to the negative charge, while the electrons are going to be attracted with a greater force to the positive charges. Eventually, because now we have such a huge electrostatic attraction here, because of that, that's what is going to cause the leakage. Because the distance now from these negative charges that you can see at the bottom to the positive charge is going to be closer through the dielectric itself. And that's what's going to be causing your electrons to jump into those orbits, into those valence orbits, so they can make their journey all the way to the positive plate.
Garcia, can you repeat that again? You lagged out again.
Okay, perfect. So I said that, okay, so you were able to see that the electrons, excuse me, like the nucleus here, is going to be getting closer to the negative plate. I mean, this is the dielectric material. When the dielectric material is under stressed, the reason why the dielectric is under stressed is because now we have a highly attractive force on the negative plate, and those nucleus are going to be attracted to the negative plate. Because of that, I said, eventually the electrons, they are going to be leaking into this orbit so they can make or complete their journey all the way up to the positive terminal. Do you hear me now?
Yep.
Yep.
Yep, makes sense.
Thank you. So thank you for letting me know. That's what I mean. Okay. So now, stretchings of the dielectric, it can be compared similar. It's going to be something similar to a bowstring with an arrow, and then you are pretty much, this is going to be an analogy. Okay. Like in this case, this is how your dielectric is going to behave. It's going to be under stressed because of the charges. Like if you think about it, eventually, of course, you know, like in the case of the bowstring, when we let go of the arrow, because this was pulled with a huge force backwards, the arrow is going to be able to be shot. In the same, but in the same token, the electrons here, I mean, they are being attracted. Excuse me, like, I shouldn't say the electrons. I should say that the nucleus is being attracted, causing this electron pretty much to be able to shoot right into the orbit. So they can make their trip, so they can travel, and they can journey towards the positive side. Or
can you zoom out of your screen there? I can't really see a picture.
Pardon me?
Is there like supposed to be a picture on the screen?
Oh, you don't see any picture on the screen?
No, you're zoomed in.
I see it.
I can see
I
that.
see it fine.
I see it too.
I see it fine. Yeah.
Oh, there we go.
I think it's just you, Nico.
Okay, now you saw it. Thank you. Thank you for the feedback.
My bad.
No, that's okay. It's good.
It's also up on Econestoga if you guys want to follow along.
Yeah, it's on Econestoga.
Okay, perfect.
Okay, so anyways, what we are going to do at this point in time, okay, so I'm going to be showing you this, but instead of showing you this slide, we're going to see this with this, okay?
You cut out again.
I said that this slide, instead of discussing what this slide is all about, we are going to see it in multi-sim, because that way we can see the animation.
Okay.
Now, the dielectric. Air is taken, and of course, we know that when it says air, we are talking about dry air. There's no any humidity in this air. This is just pretty much pure air. It's going to have a dielectric constant, which is equal to 1. So depending on your dielectric constant, the higher the constant, the higher also the capacitance that you are going to be able to have on your capacitor. Remember that one of the factors that determine capacitance is going to be the strength of the dielectric. So air being 1, and then from there, like different either materials or liquids are going to have different dielectric constants, which is going to, you know, like to give us more or less capacitance. Any, like, can you check here, like in the case of ceramic is like 1200. That's a very, I mean, like ceramic has a very, very high dielectric constant. Now, wonder why is it that high power transmission lines use like ceramic insulators? It's because it's pretty much the best insulator, one of the best insulators that we can find.
Porcelain.
Pardon me?
They use porcelain.
Porcelain is made from ceramic material.
Yeah.
Yeah.
So anyways, yeah, but that is true. You know, that's what we call it, porcelain, right?
Mm-hmm.
Yeah. But it's a ceramic material that as well, you know, so because here we also have like pure porcelain. It's going to be like 5.5, while ceramic is going to be 1200.
Oh, that's kind of weird, eh? But they call them porcelain insulators whenever you order them.
Yeah.
Huh.
Anyways, so let's get moving. So this is something that you already did on, I mean, like in theory, which is like determining the total capacitance when you have a few capacitors connected in parallel. Why is it when we have capacitors in parallel, the question that I want to ask, why is it that capacitance add up? Like in this instance, having your 20, 30, and 60 microfarads capacitor, we can see that they are in parallel, but in that instance, our total capacitance is equal to 110 microfarads. Any idea on why that's happening? Why do they add up? Because before, when we had resistors, that had been the complete opposite. The resistance was going to be smaller, you know, in the case of resistors, and also in the case of inductors. But in the case of capacitors, the capacitance, the actual capacitance is going to be adding up.
Is it, I don't know, I'm going to take a guess. Is it because when the capacitance are storing the charge, they're going to discharge it all at the same time that way, so it's added up, whereas if it was in series, they would discharge into the next one?
Perfect. Perfect. I couldn't say it better than that. Perfect. Absolutely right. So we could see it also from the point of view that the area of the plates is going to be adding up. And now that all this is going to be combining each other like a huge plate, like a huge plate on either side of the capacitors. So because the plate area has increased, also we could see it from that point of view, we have been able to increase capacitance. But I like your analogy. I love it because by the same token, like when we have batteries connected in parallel, we're going to have a higher current output because they are connected in parallel, even when they have the same voltage for all of them. We're good there?
Yep.
Good. So the last slide, and then we're going to move into multisim. So in this case, we have the capacitors connected in series. However, we can see that the capacitors in series, they are going to do the complete opposite. We are going to be using the reciprocal formula. And instead of having a higher capacitance, like before when they were connected in parallel, we were getting 110. Now we are getting only 10 microfarads. Why? What is one of the factors that determine
the distance between the plates?
Perfect. So when two capacitors are connected in parallel, that distance between the plates has increased. And because we have increased the distance between the plates, we have reduced capacitance. Somebody was asking me, like in another class, okay, so when do you ever need to use a capacitor connected in series? And I responded, well, like if you need to reduce, like if you have capacitors at home and you need to reduce your capacitance because anyways, you don't want to have a leading power factor, then you would be connecting your capacitors in series. That's number one. And number two, as I was mentioning right at the beginning, because you are going to be using the capacitors to create a phase shift in motors, depending on the amount of capacitance that you have, you are going to be able to control what is the angle of the phase shift that you create regarding the start winding and the run winding in any capacitor start motor. So one last slide, you know, because I don't want to say this, I don't just want to go through this without covering this super quickly. Like right here, this is also important to know. What is 1 farad? That's how capacitance is measured in farads. And a capacitor have a capacitance of 1 farad when a charge of 1 volt across its plate results in the movement of 1 coulomb. That's very interesting because, in other words, if we have 1 volt and 1 amp in a capacitor, you know, then we are going to have a capacitance which is equal to 1 farad. Any questions about that?
Nope.
Okay, so anyways, now let's get, let me get you to multisim. What I'm going to do now, okay, let me show you. This is the lab. Can you see that?
Yep.
This is the lab that you are going to complete once we are able to go back to the college. In this case, you are going to be using your transformer module, a lamp socket, and you are going to use different light bulbs, all the way from 25, 60, and 100 watts, all the way, I mean, even up to a 660 watt heater. Like the reason why you are going to be using all these different loads with your bridge rectifier that you have right there is because by doing that, you are going to be able to see with your 500, you are going to have a 500 microfarad capacitor. Okay, that's the 500 microfarad capacitor. That way, you are going to be able to see on the oscilloscope what happened to your ripple voltage. Okay, now I'm going to give